Hi everyone, thanks for joining me. So here to talk about Alchemy meets science, adopting Elixir in cancer therapeutics research and development. So who am I? Human being, hopefully not a robot. Father, recent father, less recent husband, half Swedish, half Dutch, and all Canadian. So I work for a company called Zymeworks. The mission at Zymeworks is to develop therapeutics for various ailments and to hopefully send people back to their loved ones. Right now our focus is on cancer treatments. And so we're using an engineered antibody to do this. So there won't be too much biology, I promise, it's just a few slides, just to give some context over what we're doing. So the molecule that you see on the left there is an antibody that your immune system naturally generates. We represent this in a diagram form by this little Y symbol that you see on the right. So antibodies, those two little ends of the arms there, will bind to specific locations on the target cell, other protein, anything else that goes on. But those targets are really, really, really specific. We're talking about like one very specific location on the surface of a cell. And so your body will typically generate a number of different antibodies for the different targets that they want to do. But what if you could build an antibody where those two arms targeted two different things? Now you can specify two different locations on the same cell and get a higher specificity of what you're going after. So there's less chance of your antibody binding to a healthy cell as opposed to the cancerous cell. So Zymeworks has two bispecific antibodies that we've engineered that are in clinical trials right now, ZW25 and ZW49. And so this is kind of a diagram to show what we're seeing here is the surface of a cancer cell, and the little trees there with the white and green are receptors on the surface. And your typical monoclonal antibody, as they call them, where the two arms grab onto the same thing, will bind to two of these receptors and sort of take them up. And so nothing else can grab onto them. But with ZW25, we can actually bind to two different locations on that expressed protein. And you'll get a higher density of the antibody that grabs on. So you get higher efficacy of the drug. So that's all the biology that we're going to go into, so don't worry. So what we've been able to do at Zymeworks is divert a lot of the modeling work and the design work to do that in silico. Lab experiments are really, really expensive. And so if we can front load a lot of this design work into computer modeling, we can save a lot of money and give a lot of benefit to our scientists. And there is a wide array of tools and applications that we use to do this. I'll get into our app framework later, but at last count this morning, we had 170 apps available on our compute cluster, and so they all do widely different things. And so there's everything from analyzing the sequence of it to analyzing the structure, molecular dynamics, and everything in between. So here we're looking at just a graph of the employees. So all of our tools are used internally by our scientists and by people at the wet lab. And over time, we've had a fairly static number of software developers, the people that work on the infrastructure, that work on the web services, and the libraries and the frameworks. So that's the blue line in this chart. The green bars here are our scientists that contribute to the scientific aspect of the code base. So they're the people who actually know the ins and outs of the scientific validity of the code. Purple are the protein engineers, and those are the primary users of many of our tools. Discovery research is a new department that you can see is growing rapidly. But this represents most of the users that we have. So it's not that we have to serve tens of thousands of different users across the world, we have a wide array of concepts with a small amount of users. So just a really quick demo of what this looks like. Let me see if this will mirror. Cool. So this is one of our basic little single-page web apps that just exposes one of these scientific applications to the user. So they will select a file. This file, what we're looking at is, it's a data format called FASTA. Each of those blocks are the amino acid sequences of a particular protein sequence, and there's some information in them. And you can number the positions of these characters in various different ways. So we're just going to go ahead and load in all the data, make sure that it looks okay. We're going to call one of these scientific applications to do the processing for us, and then we can interact and view with the results. So this is kind of the standard process of what we do with our web apps. But I, as the person who builds the infrastructure, I don't need to know any of the scientific code. So that's more or less what that gives us. Okay. Where did my cursor go? Cool. So, like I said, we just had user with a web browser. They interact with our sort of portal that we call Hub, because why not? Hub happens to be a Go-based server right now. And then that ultimately talks in the background to what we call our ZappServer. Zap is our Zymeworks applications. ZappServer is now written in Elixir, but it ultimately calls the Python scientific code in the back end. So what are the things that we have today? We use Python for our entire scientific stack. There are a number of benefits to using that. We have a lot of people that come out of academia, and they know Python off the bat. So it's really easy to just get them up and running, get them working on our code. We still have the ability to optimize the performance by dropping down either to Python or C++ extensions. And so it's the de facto standard. So we built a little application framework around that we call Zap, that means we can, in a introspectable and declarative way, define the application arguments. We handle command line parsing for them. It's a standard template so that the scientists can just start plugging in the actual value for all of this. We also take care of handling all the logging that they need to do. We get access to the Python debugger, so it's just a good fit for us. And this is about the complexity of a very basic Zap, right? You define a dictionary in the top level of your module called arguments. You define some inputs and some outputs. We can pretend that we're all Obi-Wan and saying hello there, and then we can print the message. And so on the command line, message will be a double dash option for the user to input. And of course, you can extend this to have 10 or more inputs, a number of outputs, and anything that you want to call within the Python application. And so ultimately, that's being run by this ZappServer service that we have. It's actually two separate services. It's not that complicated right now. So we have a plug-based web service that ultimately dispatches work over to the agent, and then the agent will call via a port the Python subprocess to do the work, return the values back to the client, and display all the results. So we're in a really happy place now, but sort of how did we get here? Because it definitely wasn't this easy to begin with. So all the Zaps, we have a command line interface for them. So a lot of work that scientists would do, they'd log into the compute cluster, they'd SSH in, run the Zaps manually, take the output file, load it into Excel, make their charts. It was a lot of manual processing, a lot of manual work. So we have Sun Grid Engine, which is used to dispatch jobs. It's a distributed resource management tool. So you can submit a job to the cluster. The cluster manager will find an appropriate agent to run this on. It'll dispatch the work there and then tell you when the job is done. And deploying all of our code involved just installing RPMs on all of the compute nodes. So every time that you wanted to make a bug fix, you'd have to dispatch and deploy all this code to a small compute cluster. And so we built the first version of ZappServer just in Python because we were familiar with it. It was sort of what we were used to. It was specifically Pyramid. So if anybody's used Pyramid, you just have a request handler that is a function call. we would load the module by name from the request, execute it, and then return the results. But there was no scheduling, there was no throttling, nothing of that sort. You'd have a 4-core machine, and you could easily hammer it with 50 requests and just tear the whole thing down. And because everything was tied to the available Python code on the service, anytime that you deployed new code, you'd have to restart the service. So you got this sort of dependency chain of make a bug fix, you have to now touch the web server. But initially, the number of users was pretty low, so it worked out fine until it didn't. So things quickly grew out of hand. We developed more of these web apps. We got more users using this, and eventually we needed to take care of actually scheduling these jobs properly. So we did the reactionary thing and said, okay, well, what's something that'll handle this for us? And Mesos was a new technology at the time, and we had a couple of developers, and they gravitated towards it. It seemed to tick all the boxes that we really needed. And so it's similar to Grid Engine, but it's more meant for those quick dispatches. Grid Engine scheduling at the time was pretty low frequency, so it wasn't really that you could rely on it returning a response within a few seconds. And same kind of idea. You would have this generic tarball of code, and you could run it somewhere on a remote host. And so the plan was to rewrite the entire service using Mesos to do this distributed computing for us. And so this is kind of how we broke down the application. You'd have this master service or master application that would be your HTTP API, and it would then dispatch all the work to Mesos, and then Mesos would find an appropriate agent, run the code on there. And all the code was distributed using what they called their executor tarballs. So that was actually kind of a nice thing, because we could just easily repackage a tarball. It would be pulled down from a web service, unpacked, and then executed. So we didn't need to do all these redeployments all the time. We just had to publish a new artifact. Mesos also gave us the ability to scale. You just add a new agent, and it registers itself and does a whole lot of work. And we decoupled the web services from the scientific applications again. So that was another big benefit. We could just treat our web service as just the web service, and the scientific apps as the scientific apps. So that was a really good benefit for us. And decoupled the deployment of the web apps themselves. So if we needed to actually fix the web service, we didn't have to go and worry about the impact on the scientific code. And another big thing that we sort of realized after this, with proper job scheduling and just queuing things up and not overloading your services, we only needed a single 8-core instance to handle our compute capacity. So we didn't actually have that big of a scaling problem. It was more just sort of having something to manage the throttling. The problem with Mesos for us at the time was it actually is a little bit more in terms of infrastructure that you need in order to get going. If you want a high availability Mesos cluster, you need 3 Mesos masters, you have to have Zookeeper running, you have to have this, that, and the other. There was a lot of complexity and responsibility that we had shifted onto the ops team, which wasn't all that great. And they weren't all that familiar with it. They were used to just your standard Linux system. And then we started to have some issues with uptime, and we weren't really sure about why. This was a pretty young service, or young application. And so we started to get issues where Monday morning you'd come back and all the agents would be deregistered, and so nothing would be accepting work. And that would happen a number of times per week. Sometimes just all these pieces wouldn't really play nicely with each other. And it got to be a big problem where people would go and run a scientific app and they'd get some generic error, and it was really difficult to figure out why. And especially because it's this large architected framework of a service, then we had no real insight as to what was going wrong and what was happening. So the half Swedish side of me, the Swedes have this term called lagom, which the best analogy that I can give is Goldilocks and the 3 bears. You've got Goldilocks that shows up, Papa Bear's bed is too hard, Mama Bear's bed is too soft, Baby Bear's is just right. You want to find that just right solution. So that's what we tried to do. We tried to say, okay, well, we went from something that had no scheduling, no throttling, no nothing, to way overcomplicating the problem. What can we do that's somewhere in between? And so my coworker discovered Elixir. And I said, okay, well, this sort of seems like it fits all of the things. We can communicate between different nodes if we actually want distributed computing. We have process supervision, automatic restarts. If something goes wrong, just bring back the known good state. We had observability, logging as first-class citizen. And we were the ones that were writing this and developing this. And so again, just bringing this back up, like this is about as complex as it is. We really didn't need all that much more. And so I ended up writing this in early 2017, just plain plug HTTP server. We only had about 800 lines of code for both of those components. We kept the HTTP API the same so that we could just drop in this replacement. We reused the same executor tarball model from Mesos because we already had the build pipelines. It seemed more or less okay. Deployed the first version of this to our systems in July of 2017. And from the ops perspective, it was one host with 2 RPMs and 2 services. So they were super happy to just tear down everything else. And we only had one show-stopping bug for this whole thing in February of 2018. So that was basically 7 months of uninterrupted uptime. Going from it failing twice a week to this was a huge win for us. And last I checked, it hasn't been touched since March of this year. So it's one of those great services where we've developed it. It does exactly what we need it to, and we've been able to forget about it, which is awesome. So that's not quite the end of our relationship with Elixir. Like, that's just one case, and we now want to do more with it. So there are a couple of limitations that we have with ZappServer in its current form. All of the HTTP calls to ZappServer are synchronous. So we're holding open that connection, waiting for that background execution to finish, and then returning the response, which means that if you have something that takes more than about a minute, the connection times out, and users get unhappy. The communication between the port and the underlying process is done using packet communication. For those unfamiliar with this, you have a message of a certain length. You prefix the length of the message to the message, and then send that whole thing along. The recipient will take the first 4 bytes, decode the length of the message, and then continue reading that much more. If anywhere in the Python side of the code you had a print statement, that print statement is no longer prefixed by the length of the message, all the communication goes haywire. So, and in this particular setup, we were limited to just our Zapps framework that we had set up. We wanted to generalize this so that we could run any of our computational workflows. We have a number of scientists who want to use R for their mostly stats work, and just anything else. We wanted to generalize this in case we had another type of task that we wanted to run. So what if we could run our tasks asynchronously? You submitted a job just like we would do to the compute cluster and check back on the results later. The ability to log our results properly and inspect those logs as a first-class citizen. Persisting the outputs, making sure that I can run a job, a scientific application now, and both return to the result or share the result with something else. Because in ZappServer, the response is coming back specifically to me, I have no way of sharing that result with one of my coworkers. And then, like I said, we wanted to generalize the definition of one of these tasks. So this is just a small diagram that we can generate from our scientific workflows. In this particular case, it's just a greeter. We have a small case statement in there that will let us say, is this user named Bruce, and we'll actually say hello Batman, because we know his secret. And then we can extract all the results out of this. And this is a super simplistic example. In this case, that greet block would be one of our applications or a Python function that we would want to run. But these things can get really, really complicated really, really fast. So this is another example of a computational workflow that we have. For reference, each of those large green blocks in the middle of the white block, those are also their own workflows that have their own nodes inside of them. And so it's turtles all the way down. And so this is an example of something that you'd want to submit, and you'd want to say, okay, well, please run this, and I want to come back to it in 4 days when it's actually finished. And then I want to be able to load the results and share them with a colleague. So we're developing a new service called TaskServer, using Phoenix as the front end. It's a nice, clean way of doing things. And generalizing the term task. We're not actually using Elixir tasks for all of this. It's the name that we came up with internally. Logging them properly, and then we can implement different backends for the task execution. So we can either run these things locally. In development, I just have a virtual machine on my Mac, or in production, I can plug into the compute cluster. But that leads us to So back to Grid Engine, we have a Grid Engine cluster. There have been a couple of updates. And for the long-running tasks, the things that take minutes, hours, days, weeks, you don't really care if it starts right now. So we can actually differentiate between the things that we expect to start and run immediately versus those that need to take a little bit longer. Some of the newer versions of this have the ability to make the underlying process run as a specific user, which is awesome for our ops team because then that means that they can implement quotas for different users, fairness policies, all that kind of thing. We wanted to make sure that rerunning a task, restarting a task works as expected. And this is exactly what Grid Engine does well. Like, this is why academic institutions use this for everybody at a university. You'll see Grid Engine or PBS, Torque, Slurm, Maui, Moab. There are a number of different implementations that all do a similar concept to this. And so if we can plug into Grid Engine, then we can just dispatch all the actual execution work to the compute cluster, and it'll take care of that for us. So to interact with Grid Engine via an application that uses, so we just call it DRAMA for lack of a better name, the Distributed Resource Management Application API. And so there are bindings that you can plug into this API for C, Java, Python, Go, a bunch of other languages, but nothing yet for Elixir until soon. So this is another initiative that I'm working on right now, is actually writing one of these libraries so that you can just call the DRAMA API directly from Elixir. So if you need to integrate with one of these compute clusters, check back on Hex in probably a couple months once I've actually locked the thing down, and you'll be able to tie in with that. So a couple of lessons learned just from sort of where we came from to where we are now. Being boring is really good. Services that you set up and spin up and forget about are one of the best things ever. And when you're evaluating a new technology, something to solve a problem that you have, what is it that you're actually wanting to solve? Just because something's new and shiny doesn't mean that it's going to actually be better for you. What new challenges are you introducing by adopting a new technology? So with us, with Mesos, we ended up shifting that complexity onto the ops team. And I don't think that they had really signed up for that at the time. So that was sort of a shift that we had. And sometimes the old solutions are the best. I will harp on this for a long, long time. You can pry my headphone jack from my phone out of my cold, dead hands. Like, what are we actually trying to solve? There was a guy who actually managed to put the headphone jack back into his iPhone 7. There was space for it. There was all the wiring, everything else. So boring is good. And right sizing is pretty hard. Like, when I say right sizing, I don't just mean scaling out the number of compute resources. There are a number of different dimensions to this problem. You have, obviously, the compute resources. You have human resources. You have technical complexity. You also have time. Like, how much time are you willing to spend on a solution? Or can you find something that's good enough? Is ZappServer in its current form perfect? No. Has it worked without any significant interruption for the better part of 2.5 years? Yeah, awesome. And this is an adage from another coworker of mine. So use the tools that make the hardest part of your problem easier to think about. So we are a polyglot group in the software team. So we have Python, we have a couple of Go-based services, we have Elixir, there's a dabbling of Ruby, and like I said, the R scripts. But that tool that makes that hardest part of your problem easier to think about is going to be a big win for your team. Don't be a pure Elixir shop just for the purpose of being a pure Elixir shop. If that solves your problem, great. If there's something else that will solve your problem better or make your life easier, consider adopting it. Again, consider, don't just do it. And try and find logom things. There's sort of this, you ain't gonna need it mentality. We ran into this ourselves, but try and find something that fits just right to the problem that you actually have. And it'll probably mean that you don't create a problem for you to solve tomorrow. So, and that's the end of my talk.